or XCDS, X-ray electron dispersive spectroscopy. Okay, XCDS. I don't know how many of you know the Barry Carter books or microscopy, the big books for material science. So he used always XCDS, XEDS, X-ray energy dispersive spectroscopy. So EDS can be collected, the X-ray can be collected at the EDS, and yields electron energy loss spectroscopy. The lost electron, which electron coming from high energy electron coming from top to bottom, and then interact with sample, then pass away. This lose some energy. This electron can be plotted as a function of energy loss with intensity that is called yields. So everyone has, EDS has chemical informations, and also it has lower resolution than yields. And yields has a limitation of a range, so it cannot be, so here you can use 20 kV or 30 kV X-rays collection, you can have larger range, but yields has a limitation of 0 to 2 kV range, but it has a much better energy resolution. Yesterday we are seeing that, we saw that okay, how yields can help the shift the oxidation states of your cobalt +3 or +4 or iron peak or oxygen peaks. So this can be possible in yields. We are not going for that. We are only limited by EDS, which cannot be give the chemical electronic structures informations. So for that, in EDS, everybody knows the X-rays has a energy, and each energy has a characteristic from the element. So it has bands. So each element has a lower and upper bands. So this is very characteristics. So each element has different energy. Suppose the silicon has this peak, copper has different energy. So this energy plotted as a function of the counts. So this count can be mapped in two ways. One is which element presents and how much is the present. These two questions you can ask from EDS. So first thing, which element is called, what is the elements? Okay. So here map can give what is the elements. So silicon, I'll show you a map next time, further slide. So map is showing you which element present in your samples and how much is called quantifications. So that's what, and then if you think about after loading samples, you can go inside where exactly samples inside your lenses. So here this sample is sitting inside, and these are the X-ray counter, very close to your samples. So there are 4 EDS detector around your sample. So sample is even tilted, it doesn't matter. So see here, electron beam is coming from top and passing through, and X-ray is coming from a sample. So this is the holder. You can see here, these are the grids. So you can see here, this holder, whatever tilt you have a correction factor inbuilt from the software. So after this, you can see all factors can be considered, and you have a very reliable data from your samples. So you can think about this is this is tilting necessary for your samples. So after this, you can have 4 detectors. So each detector individually collecting X-rays and forming the maps. So you don't need to think about sample tilt, sample shadowing, any angle samples. Every angle you have a data, and every high quality data which can quantifications is easy and also can be very fast. For example, here you see you have 4 detectors, and this kind of map can be collected in a minutes, 5 to 10 minutes. Okay, before it was 40 minutes. When I was a student, it was 40 minutes collection of sample in spectra. For example, I can give one example. Let's say how the element distributions across your space samples, and then you can have a small specific as well. So you can have also atomic resolution map interface. This is, I would say, is qualitative way. I cannot believe on quantification of this HRTM image. HR had of HR EDS maps, but after this, what is more? What is more in that? Because distribution is more, and it can also can be battery material, can be find what is segregation in that EDS map. You can see here, segregation is very prominent here. You can have charge discharge cycle, and you can see how this element behave in EDS. The segregations, you can find 4 cell structures. You can see particles. This is particles, and you can find how the cells, nickel and silver, how the core cell structure looks like here. Further, you can have interface. These are the atoms, okay, here, this is spending it on that. So here, these are dark sides, so this is the interface, so there are and dark, and even darker. So this is the interface, each atomic column. So how can I see without compositions? So this is more heavier than these people. Okay, so now EDS also shows different color, titanium, strontium, yttrium, barium. So this is a doped semiconductor samples. So interface can be also mapped in such a beautiful way. So you can see single on the sample interface. So this is seeing the image, you cannot EDS map to see how variations across the interface possible. Okay, now this is a 2D image. So now you can say, Shyam, 2D is possible. So what is that? I cannot have 3D informations. Information means, so EDS, first thing, back I can, before going to 3D, 2D you can get which element presents and what is the present, how much is the present, okay. You can get all information from EDS or XCDS. So my question is now to all of you. You have this image. With some particle inside. So this is 3 possibilities. Tell me, after seeing the image, can you answer these questions, whether these particles are above the samples, in between the sample, or mixed distributed samples, above and below. So you have any answer for that? Because we are seeing the projection of your samples. So whether by seeing the image, 2D image, can you answer these 3 questions? Possibilities. Answer is no or yes. Yes or no? No, yes. No, right? This is definitely no, because this cannot be possible, because we have, if you have sample like that, you project image like this. Sample is inside, you projected image, you can see similar image. Randomly distributed particle, you have above, below, you projected image, electron beam is coming from top, projected image, similar one. So to answer that one, we need a 3-dimensional image of your samples. It's called tomography. Okay, so how it is doing? It's very simple. It is tilting your samples, different angles, and collecting the image, which is plus minus 70 degree. For example, this is normally all tilting, it's collecting 2-dimensional projection of the samples, and after software it can bind and forming the 3-dimensional image from the projections. So first thing is 3D to 2D object, all 2D object to 3D dimensional image. For example, tilting angle is plus minus 70 degree. So it's a general thing. You can choose as much as possible from your samples. This involves not only the software, hardware, microscope, and also it is a expensive process. So I can give you how this looks like. So for example, look, this is the samples. It has some dark dots. Okay, I can play one more time. So this is a different projection image. You see different projection. This sample is tilting across the rotation axis. You can see here now. See, rotation axis. Its sample is tilting and collecting different angles, like here, like this. Okay. So this is the angles. So you can see like this, and sample is rotating. So I have 3-dimensional informations. Up to here, microscope is possible over. After this, there are 2 processes. I will not go for reconstruction process. You can see ultimately there are particles. This is a bacteria samples. See, particles all around distributed up top in between. So with the only 3 dimension, it is possible to have answer such a questions that we cannot answer in 2-dimension projections. So 3-dimension process is called tomography. It is also possible in TEM as well as STEM. And also parallelly, to extend that one, we have a EDS tomography. So composition in 3 dimensions. So how is possible? Look at here. So now we have a samples, you know, battery, superalloy or core cell particles or catalyst. So you know where exactly the catalyst particle, how the shape looks like, what is the composition difference in superalloy. All this possible in 3 dimensions, and you have a much better answer from your questions you ask to solve your problem, research problem. Anyway, so this is what microscope all about to you. Yields is even bigger picture. And before going to the last part, I would say you now go to the microscope slot, you know what to do, how to get solved your problem, and you can go and ask the users to, first you analyze what can be possible in your samples, and then you tell how much time is required for that. So here you can see now, this is the all things we discuss from the top: imaging, TM imaging, STEM imaging, then EDS, and then tomography, 3 dimensions. So here I would like you to this is a normal strategy how to use ease of use performance. So I hope that you understand now what can be possible from your samples, and this all depends on your samples, how you do, how you analyze. Make sure, only thing is first last words, make sure that you are interpreting right way, either in your brain or the software, you know what you are doing. Now in AI ML world can interpret anything from your image. So if you ask these people, I want ChatGPT, okay, I want to do some interpretations. So that day we tried with all fun with students, always. So I tried ask ChatGPT to put the image, interpret the image. So one time it's don't know what to do, right? It has idea about what ChatGPT. I put an image. I said, please interpret this image according to diffraction pattern or composition, whatever. It did something. No, lot of English literature and problem, but some words are correct, some words are very wrong. Okay, so I would request you people, I know you are very smart people, smart researcher than us or older generations, but I would say be careful when you're using your any data to online or AI interpretations. Okay, try to understand yourself, try to feel your samples, and then microscope can help you complement your data and you publish your good publication data and journals. Okay, thank you for that, for kind attention. So afternoon maybe we have I don't know, half of people are going demonstrations, and also if you have any queries you can discuss anytime in a specific sample. If I have idea I can share with you. Yeah.
If you have any queries related to electron microscopy,
you can have a discussion afterward as well, because sir, if you are normally going to GSI lunch, all this stuff, so in demo also you can ask.
yes.
Yeah, no problem.
I think they can split into 2, and please, yes, yesterday GSA batch, like yesterday.